Apply heat to the iron until it's red hot. How hot? Well, you know you can measure hotness with a thermometer. But you can show hotness by using a thermographic camera. Watch this. So what is hotness? And why is it spreading out like this? Let's start again, but this time with the atoms. This model shows iron atoms in a piece of iron. They're always moving. They have kinetic energy. Hotness is a measure of the kinetic energy of atoms. We'll apply heat to the weld area. Some of the hotness is transferred to the iron atoms. As their kinetic energy increases, so does the temperature of the metal. In the area of the weld, the atoms move so rapidly that the state of the metal changes. This is a light microscope image of a weld. The lower piece of metal melted, and then the upper piece of metal was pushed down into it. At very high temperatures, the atoms of metal have so much kinetic energy that the solid metal melts. Further away from the source of heat, the metal cools down and solidifies. Where did the hotness in the hot spot go? The atoms in the hot spot have a lot of kinetic energy. As they rush about, some of their energy is transferred to the slower atoms in the cooler surrounding metal. As that energy spreads, temperature differences in the metal tend to even out. In fact, all energy tends to spread out and become less concentrated. This is called energy transfer. As the welder applies the flame to the metal, energy concentrated in the flame transfers to the metal and does useful work. Unfortunately, whenever heat is transferred, some of it is transferred to the environment and becomes so dilute that it can no longer do useful work. This is called lost heat. In many situations, it's important to control the amount of heat transfer and the amount of heat loss. Often, the designer and the engineer try to reduce both. Why should that be? Can you think of any examples? Here's the 840 to Peterborough. Switch to thermography. The hot areas are light, the cold areas are dark. The engine looks hot as you'd expect, but look at the wheels. They are literally glowing with heat where they run on a steel track. Why are they so hot? Where any two surfaces rub together, friction causes heating. Some of the kinetic energy that would have performed useful work is being transferred to the wheels, causing them to become hot. That heat is lost into the cooler surroundings. The thermographic camera detects it as it radiates from the wheels into the air. It takes energy to do any kind of work, such as drilling a hole. Now watch this. Heat is being generated and then lost into the environment. That means there's less energy available to do useful work, so the drill's efficiency, like the trains, is reduced. Could we improve efficiency by reducing the amount of heat being generated? How would you reduce it? Look at those piston rods. Removing metal surfaces seems smooth enough, but magnified 10,000 times, you can see how rough they really are. Oil forms a film over the surface of the moving parts and keeps them apart. The friction and the heating is reduced, and mechanical efficiency is improved.
Bernal made a sunny June next week at the slightly later time of 4.
Take one cube of titanium metal. Drive it towards another cube of titanium. We'll start it vibrating at a high frequency. What happens when the two pieces of metal meet? At the point of contact, kinetic energy is transferred to the atoms in the metal, so that the temperature of the metal rises until it melts, creating a weld. Friction and heat transfer can be very useful. But heat transfer doesn't only occur with friction. The electricity that drives the friction welder comes from an electrical substation many miles away. What do you think happens when energy is transferred as electricity? High voltage transmission lines. Switch to thermography. You can see that the live lines on the right are hotter than the unused lines on the left. Energy is transferring from the hot live lines into the cooler air and is lost. High voltage electricity is dangerous to work with, so the high voltage is transformed to a low voltage by transformers, like this one. And, just as you'd expect, some of the incoming energy is causing the transformer to get hot. Less than 0.5% of the energy is causing heating, but that's enough to cause serious damage, unless the engineers can get rid of it. How do they do that? Heat is generated in the transformer's iron core and copper winding. To carry the heat away, the engineers place the transformer in a container of oil. Heat travels into the oil, and then to an outside surface where it's lost into the air. How would you increase the rate of heat loss? In large transformers, heat loss is increased by increasing the surface area with cooling pipes and using pumps to increase the flow through the cooling circuits. In very large transformers, fans blow cool air across the cooling pipes. The engineers went to a lot of trouble to increase the rate of heat loss. But what about the enormous amounts of heat loss that take place at power stations, where the electricity is generated? Although modern power stations are efficient, Quite large amounts of energy are generating heat which is transferred to the environment and lost. Here, the engineers do their best to reduce heat loss. Where does the heat loss take place? This is one of the main boilers. Powdered coal is blown into the boiler and burned at up to 700 degrees Celsius. The potential energy in the coal is transferred as heat to the water in the pipes which line the walls of the boiler, increasing the kinetic energy of the water molecules to produce steam. Now we're inside one of the boilers, which has been shut down for maintenance. Each boiler is as tall as a 6-story building. The kinetic energy in the steam drives the turbines and the generators, where it is finally transferred as electricity. The exhausted steam is cooled down to water in the condensers and returned to the boilers. We'll get a better view of the power station from above, and to see where energy is being lost as heat into the environment, we'll change over to the thermal camera. The smoke from the chimneys looks hot, but there's a little heat escaping from the top of these cooling towers too. It's not smoke, so what is it? Here's a diagram of the cooling circuits. When the exhausted steam leaves the turbines, it must be cooled down to water before it can be pumped back to the boilers. This is done in the condensers, where heat transfers from the steam in the boiler circuit to cold water in the cooling circuits, raising its temperature. If the water in the cooling circuits gets too hot, it won't cool very effectively. So how can heat be lost from the cooling circuits? The water is pumped into these enormous towers and is air-cooled before it returns to the condensers. The cooling towers are designed to transfer unwanted heat from the cooling circuits into the environment. Here's another power station, near London this time. Notice any difference? No cooling towers. If you wanted to use the environment as a heat sink, somewhere to get rid of unwanted heat, how would you do it? No need for cooling towers when you can draw cool water from the Thames and pump the warmer water straight back into it. You can see the warm water forming a plume downstream from the outlet in the river, cooling as it becomes more dilute. Pouring heat into the environment is sometimes called thermopollution. What do you think it's doing to the local plants and animals? Certain water plants and some animals, such as these caddisfly larvae, thrive in the warmer water. Mayfly nymphs increase their numbers dramatically. So do the leeches. Most species of fish, such as trout, decrease in numbers in the warm water, but grow more rapidly than normal in the cooler areas downstream. At the warm water outlet, the highest temperature is red, cooling to brown, and then to purple. Why should the different species be distributed in this way? Could the waste heat from power stations be used for anything?
keeping temperatures below freezing.
Some power stations sell their waste hot water to local homes and factories. And what happens to it there?
So it should become lighter.
We'll use a different kind of thermography to show that in these hot water pipes, heat is lost into the air. Flowing from left to right, the water gradually gets cooler. The top pipe contains the same hot water, so why should it look so different? It's insulated. The surface is cooler because the insulation has reduced the rate of heat loss. And because the pipe gives off less heat, its contents remain hot all the way to the shower head. Can you think of any other examples of heat loss in your home? Here, energy transfer is causing light. What else do you think might be happening? About 10% of the energy entering a light bulb gives rise to light. The other 90% generates heat. Lost heat? Well, that depends. With a little imagination, that heat could be used to cook dinner. Can you think of other ways of using this energy before it's lost into the environment? If a house is well insulated, the heat given off by electric lighting can heat the whole building. Most of this house is insulated by a thick cover of earth, like the insulation we saw around the hot water pipes. Here's a situation where we want to reduce the amount of heat loss out of the building. Can you think of any others? Whenever anything happens, energy is transferred from one system to another. As that happens, heat is generated, which is eventually lost into the environment. How's it happening here? Or here? This is the generator that powers the thermographic camera, and it too is giving off heat. Here, the energy concentrated in the branches of an old tree is being released by burning and transferred to the night air. As the energy transfers, it causes light and heat. As it transfers, it spreads out and becomes less concentrated. Wood, coal and oil are all concentrated sources of energy. So are the sun and stars. If all that energy is transferred into the surroundings, one day everything will be at the same temperature and everything will stop. Or will it? So what is hotness? And why is it spreading out like this? Let's start again, but this time with the atoms. This model shows iron atoms in a piece of iron. They're always moving. They have kinetic energy. Hotness is a measure of the kinetic energy of atoms. We'll apply heat to the weld area. Apply heat to the iron until it's red hot. How hot? Well, you know you can measure hotness with a thermometer. but you can show hotness by using a thermographic camera. Watch this. Some of the hotness is transferred to the iron atoms. As their kinetic energy increases, so does the temperature of the metal. In the area of the weld, the atoms move so rapidly that the state of the metal changes. This is a light microscope image of a weld.